Senop is making a frame-based hyperspectral camera that actually gives the new dimension for the state-of-the-art hyperspectral cameras, because traditionally hyperspectral cameras were like line scanners, and these are very good for a certain application, but they definitely have limitations for field use or UAVs or any use where the platform is not stable. But we have developed this kind of hyperspectral camera that is frame-based. So when it's the frame-based, it gives you a lot of flexibility for handheld use, for UAVs, any kind of use where the camera is moving during the imaging. And we have used it very much with the multirotors and fixed wings all over the world. We have sold this camera to the first camera was actually sold to New Zealand, and some cameras to US and South America. So we have a very wide market at the moment. The heart of our camera that makes it actually a frame camera is tunable filter that you can see here. So when the white light is passing the filter, with this kind of tunable filter, we change the light that is coming through the filter. So practically, there is a small air gap between the semi-transparent mirrors, and when we change the air gap, we change the wavelength that is passing through the filter. Of course, naturally, this leads to the situation that different wavelengths, they are actually measured slightly different time moments. So if we have these colors here and they go through the filter, yellow is measured at time moment 1, green, 2, and so on. So different wavelengths are measured slightly different time moments. But at the moment, or in the next product that we will be launching very soon, the speed is about 200 frames per second, so it's quite enough for most of the applications. So, maybe you have heard about Fabry-Perot filter technology, and probably you have also heard about some special features that Fabry-Perot filter has. So actually in this image you have one of those. So if we are, for example, measuring this wavelength, this Fabry-Perot filter will transmit different orders of this wavelength through at the same time. And of course, when we are measuring spectrum, we don't want to measure any additional peaks. We want to measure only the peak that we are looking for. So, it's not actually very easy task to prevent them, but we have a physical prevention for those side peaks. So when we measure one peak, we really measure only one peak, and this prevention number is OD4. So it's this spectrum is really poor. In some other technologies, there will be this kind of additional peaks. So please do not think about those things when you are talking about our technology, because we really don't have those side peaks. We have blocked them out. With OD4, that should be enough. Well, someone of you may think that if you have something moving part in your machine, how exact is the tuning for passing wavelength? So here we have made a comparison between argon reference peak from argon reference lamp, and the literature says it should be 763.51, and our measurement says, after our calibrated camera says that it's 763.60. So it's really accurate, even it's that fast, and that's based on special technology that we have developed together with VTT for over 10 years, and there's also patents on that technology. So it's really clever technology. And with Fabry-Perot you can achieve very narrow bands. So this is 5.8 nanometers. So that's also quite good for vegetation studies. And then finally, but not least, the special feature that you have to think about is the pixel resolution. So even in normal RGB camera, the pixel resolution that you see is actually not true image pixel resolution, but it's the result of interpolation. So you have a green pixels, blue pixels, and red pixels, and then finally you interpolate between these pixels, and then you get the final results. But in our case, every image you see is measured with the one wavelength. Every pixel has the same wavelength that's coming through the camera. So we are not making any interpolation. Every pixel is measured. And that's a very important thing, that in some cases you may look that about 90% of your data is actually calculated, but in our case, 100% of data is measured, and that's very important for science. Well, in some cases, temperatural variation in temperature may cause problems for your measurements, because there are like changes in dark current, or the system in overall is sensitive for temperature. That's quite common in electronic devices. But we have made a thermal calibration for our camera. So as a result, between this kind of temperature range, peak wavelength variance is about that, and standard deviation like this. And here you can see how the peak wavelength measurement is changing as a function of temperature. So we have blocked this feature as well, so you can rely on this data. Okay. Now, maybe you may think that, yes, it's great device, but I'm still a little bit suspicious that if you have a flying machine, or if something is moving, and if you take the different wavelengths, different time, how that is possible to use that kind of data? Or is it like does it need very big amount of manpower to make the maps? If I buy this camera, am I ever able to make any science or any beneficial with this? If the processing takes so much my time, and I have a lot of other things to do, for example, make applications for the money. But if you look about this picture, here we have a false color image of Borneo Island. We were in Borneo Island, and platform was this kind of fixed wing. It's Mavinci from Germany, and we flew over the oil palm plantations like this. And then we have a Finnish partner named Mosaic Mill, who has actually developed software that processes automatically all the data with different wavelengths. And as a result, you will get georeference data with every pixel. Here you can see the accuracy with sub-pixel accuracy. Every point, every wavelength frame is adjusted to each other. It's ortho mosaic. We have corrected those problems that's coming from the, when it's a frame camera, there is this kind of geometrical errors that are coming from the feature that it's a lens fall of things and that kind of things. Those are corrected, and it's like an ortho mosaic. And this is without any manpower. It's totally automated process. And here are then very interesting application, at least for this audience, I think. So based on this Fabry-Perot technology, there has been this kind of measurement campaign for forestry application, where we were able to define the different tree species in Finnish forest. So based on spectral data that we gather from the trees, we were able to classify pine, spruce, birch and larch this way, and then we combined this information to the three-dimensional data of the forest. And this three-dimensional data is made with the photogrammetric algorithms, but of course you can combine this tree species information to LiDAR data as well. There's no any difference, because the data is georeferenced. Then you can combine the data with any other data, which is also georeferenced. And then the forest looks like this. There you can see where are the different tree species. And about the accuracy, when we are looking for accuracy, we have to look about if you are interested, what's the probability that if there is a pine, and when we say this is the pine, what is the probability that it is a real pine? And for the pine, it's very high. It's almost 95%. And well, actually, for birds, it's actually even 100%. So, well, I would be very happy to discuss about some of you who are familiar with this kind of industry. Is this enough accuracy already, or do we have to do some development work before you are able to use this for making individual tree mapping as a basis for your tree cutting plans? I mean, when we combine this information for the LiDAR data that you have, you really get information of your forest, tree by tree and species by species, what you really have in your forest. So That would be very interesting talk with you. And then we have heard about park beetle damage detection. We have made that as well. So, well, this is maybe not so well-looking picture, but here are the trees and these kind of taps with different colors. They say that if it's healthy, infected, dead, or if it's a broadleaf tree for bark beetle damages. And it's not only bark beetle damage that we can see with this camera. It's almost every disease what trees has. Those can be detected by hyperspectral camera if they just have some spectral features that you can see. Because with this camera we really can see the different spectral features. And normally, if the tree is affected by some disease, you have some signs in this chlorophyll area, for example, redheads. So if you can study that redheads area very in detail, you can see the differences in chlorophyll formation in that plant. And when you make a classification based on this, you are able to see quite a lot of different diseases. Well, as I said, this technology is not only for UAVs, although we have mainly used this camera for UAVs, for multi-rotors and fixed wings. This can be also used in laboratories. So in this particular case, we were able to detect the border between the skin cancer and healthy skin. So because this is frame camera, you can just take a picture of someone's face, and then when you make an analysis for this spectral behavior of healthy skin and cancer skin, you can really see the difference, and the accuracy is very high. It's over 95% is the accuracy if you made a comparison to the doctor skills, and if there are some falls, they are like true falls, or how you say. We say that there is skin cancer, but there was not. So it's quite like a safe to use this method, because it always sees the skin cancer, but sometimes it sees the skin cancer even it's not there. But as you can now imagine, this kind of new technology, it will open a lot of new applications when people just learn to use it. So here are the summary of all the benefits that I have been talking here. There's one thing that I didn't mention yet, so I want to highlight it. So it's this, it's programmable. Some of you may be a little bit scared about the data amount that this camera is producing, because there's like a 1 megapixel images, 100 megapixel images in a second. It's a lot of amount of data. So, but in our case, you don't need to measure all those 200 or 400 bands every time. You only select the bands you need. So this, you can also think this camera like a 100 multispectral cameras in one unit. So today you take those 5 bands that you need, and tomorrow you take another 5 bands. So that way it's a really good tool for system integrators or for science people. And then as a final image, I will give you some highlight about camera that's probably coming during the next year. Actually, no, it's coming. But the most difference that is have to this version that we are currently selling is that it has embedded Linux inside. So that opens some real-time applications, because we can do the process inside the camera. So that makes the data processing faster. Okay, thank you.
Thank you very much, Jussi. So, do we have questions? First here, then.
Kiitos oikein hyvästä esityksestä. Mä oon Heikki Hyyti Paikkatietokeskuksesta. In English. Okay. Yes, thanks for the presentation. I'm Heikki Hyyti from Finnish Geospatial Research Center. What does your device cost? Easy question.
Well, today it's cost 40,000 euros.
How much?
40,000 euros.
Okay. Okay.
But it's you have to think about the cost as a system cost, because if you compare for some line scanners, it's not only the cost of the camera, it's also the cost of the IMUs, probe computers, all that kind of things that you need for gathering the data. But in our case, that's the cost for the camera that is actually system itself, because it's a frame camera. It saves the data to the memory, and when you take the data out of the memory, it's ready to process. So it's only the camera, no any additional devices. If you want, of course you have to, okay, yes, you need a GPS, but that's included to the price. And then we have a relative irradiation sensor that actually measures the relative irradiation values from the sun. So even there is a change in illumination conditions, we measure the changes, and you can then use that information to make mosaic uniform. Because as you know, if the illumination of the sun is changing during your measurement combine, that naturally that makes then your map like more black here, more white here, so it's not uniform. But if you measure those changes with our sensor, then you can make the mosaic uniform afterwards.
Any other question?
Thank you for the presentation. Yeah, my question is, are you expecting to expand the spectral range above 1 micron? Are you developing other products apart from this? Thank you.
Well, yes, we have. There's a discussion about that in our development team, but currently I cannot show you any roadmaps for those kind of cameras, but definitely it's possible. And actually VTT has made already that kind of camera, and it was used for example, peat humidity detection, for example. And of course, I know there are a lot of interesting application for this 0.9 and 1.7 micron. That's very interesting area, and we are thinking about that, but I cannot yet tell you any schedule.
We have time for one question if somebody wants to. I would like to ask that hyperspectral imaging is possible to use in many different ways in forest industry. So can you say some other application which is possible to use the hyperspectral imaging than forest inventory?
Yes, in forestry or
forestry.
Well, it was that disease detection, and in overall this you can see the overall healthy of this forest. In this lunch break we were talking about that. Okay, it's if you see that you have a lot of trees in your forest, but if you don't go there and look up at the trees, you are not sure if the healthiness of the trees is okay. For example, this boreum. Has there been enough boreum for the trees when they were growing up? So that will affect to the quality of the trees. There might be like big trees, but they are not good trees because there has been a lack of some certain mineral during the growing of that tree. So, for example, in precision agriculture, when we are in the measurements of the fields and corns and crops and so on, we are able to see the total healthiness of the crops, and we are able to make this kind of variation fertilizer rate maps for the field. So we are that way seeing a little bit more than multispectral cameras.